Blockchains really suck at keeping secrets, and that is not a flaw. It's by design. Blockchains are decentralized. They are open networks where anyone can see the details of transactions. And that is great for transparency, but it's not so great for you maybe when you need to handle sensitive data, private messages, or basically anything that requires confidentiality. So this is where vetKeys comes in. vetKeys is short for verifiable, encrypted, threshold key derivation. And yes, that is difficult to pronounce. It is an upcoming feature of the Internet Computer that aims to make secure on-chain secret management possible. And while it's not officially launched yet, you can already start using it today and use it in your projects. There's a test canister available for developers, and I've been experimenting with it myself. A few days ago, I built a demo of an encrypted file transfer, a demo that lets any Ethereum user encrypt and send a file to any other Ethereum user. In this video, we are going to do a deep dive into vetKeys. We are going to talk about how vetKeys, how it works. We're going to have a look at some of the use cases it unlocks. And we will also look a bit under the hood at the code behind my demo application. So let's get started. I mean, the basic challenge is that we want to encrypt information and store it on the blockchain, right? That is the basic challenge, what it's all about. And once we have encrypted information, we want to retrieve it again, right? And we might also want to retrieve the information from another device. And number two is that we might also want to encrypt information not for ourselves, but we want to encrypt some information that is meant for some other user. So we want to be able to use some kind of identifier as an ID when we encrypt information. When doing so, we call it IBE, or identity-based encryption. Being able to more easily work with encrypted information on a public blockchain unlocks a whole host of use cases, including these, but not, of course, limited to. So basically anything that you can think of that requires some kind of secrecy can benefit from this vetKeys features. If we want to encrypt some information using vetKeys, these are the different parties involved. We have the subnet of Internet Computer nodes that make up the Internet Computer network, and these nodes host canisters, the canisters where we want to store our data, and we interact with the canister using some web-based front end. Each node on an IC subnet gets a share of the master key that we will use to derive vetKeys. It's really important to stress that no single node has access to the full key, and never will they have during the whole derivation process. The subnet nodes can jointly derive new keys from this master key that they all hold a share of. Doing this threshold signing procedure. And to be able to derive new keys, we can supply the nodes with a derivation path and an ID that allows for any number of unique keys to be generated based on the master key. Once we have generated a key, the big question is how do we transfer this key securely to the front end, and who should we trust to transfer it for us? And the answer, of course, is we should trust no one. This is a trustless environment. So when I say we trust no one, that means we don't even trust the nodes of the IC network, because an individual node can be malicious. So the nodes, the canister, none of these should at no time have access to the key that we have generated. In order to facilitate this safe transport of the key from the subnet to the front end, we create a transport key pair, where this green key represents the private key, and the yellow key represents the public key of this pair. And then when the front end wants to request the key from the subnet and the canister, it provides the canister with its public transport key. The canister passes that information on to the subnet along with the derivation information we need to uniquely identify the generated key. And that derivation ID might be a user identity of any kind. It could be an email, or it could be an Ethereum address, or whatever we like. The subnet proceeds with derivating a new key based on the derivation ID using the transport public key that we provided, which means that the key generated is encrypted at the moment of creation. So the subnet nodes never have access to the unencrypted key before sending it. So the nodes return the encrypted derived key all the way to the front end. The front end uses the private key part of the transport key to decrypt the key received by the canister from the subnet. And finally, when we have the unencrypted key, we can proceed to encrypt this data that we wanted to encrypt initially. And we can proceed to store that encrypted data in the canister. So once the data is encrypted, the whole storage part is, of course, is really straightforward. It's no longer any risk associated with passing that information around since it's encrypted. So let's circle back to vetKeyd and its components. Starting from the bottom, we have a key derivation, and that is what we do, right? We derive a new key based on these master key shares that the subnet nodes hold. We are doing this using this threshold signing functionality that IC offers, which means that none of the nodes have access to the full master key, etc. It's encrypted, which means, we talked about that. The key generated is encrypted at creation time to be able to and then passed on to the front end. And verifiably means that once in possession of the encrypted key, the front end should be able to verify not only that the right transport key was used, but also to verify that the right derivation ID was used to create this key. If we want to decrypt the data, then what do we do, right? We run the process basically all over again, and instead of using the key to encrypt the data, we will use the key to decrypt the data. And actually that takes us on to the next part of this video, where we will look under the hood at the code of the file transfer demo. On the screen, you can see two web browsers. These are two different web browsers accessing the interface of this file transfer demo. I have connected two different Ethereum wallets, and I will show you how to send a file from the one address to the other. So let's start by signing both browsers in. And we are using sign in with Ethereum. So we sign a message, and during the signing process, we generate an internet computer identity based on the signature. The interface is really straightforward. We have a send file box where we can drop a file, and we can add a recipient address. So we will copy the address from the right-hand side window and paste it in the recipient field. And we will select a file here, and we will press send. And what happened now is that this whole process of requesting a key, etc., took place behind the scenes. And we have now successfully sent the file, it says. So we'll go over to the right-hand side window and reload that and see what happens if we have something. Yes, we have a file there, the cat image. So let's click on that, and it gets quickly decrypted. And let's click on it to see if everything went well. And yes, there it is, a picture of a cute cat. So that is the whole thing, the whole demo. Let's jump straight into the code and see how all this works. I will spare you the long walkthrough of how this project is set up, etc., I can just say that it's a Vite and React application. The backend is written using Rust, and we are using also TanStack query to simplify the query handling in the front end. And what we're looking at is the use transfer create hook. It's a mutation that will be called when the user presses the send button. And the key things in this hook is us calling the backend asking for the public key. And in this case, we are sort of asking for the public key of this application. So the derived key is always tied to the canister making the call, asking for the derivation from the subnet. In our case, we generate one like main public key for this whole application. Then when using that public key for encryption, we can specify a derivation ID to tell the library which user to encrypt the information for. So let's head over to the backend canister and see how this call looks. So this call, the vetKeys public key call that we have added to the backend canister, really doesn't do much more other than passing on the request to the subnet, to the system API that does the key derivation. So we need to create some arguments where we need to specify a key ID that has an ID, and in this case it's the insecure test key 1, which is used during development, and it also supports a curve, cryptographic curve. Currently the only supported curve is the BLS curve specified here. We can also provide it with a derivation path, and which we choose not to do at this time. So like I said, we create one public key for the whole application. And once we have the arguments, we call the chain key testing canister. And of course, this call will be replaced with the real system call once the vetKeys feature has been launched. When we have received the response from the chain key testing canister, we pass that response on to the client as a vector. Moving back to the transfer create hook. Once we have the public key from the backend canister, we can proceed to encrypt the file, and we do that using the vetKeys utility library that expects to be supplied with the public key and also a derivation ID. And for the derivation ID, we use the byte representation of the recipient's Ethereum address. And we also supply it with the file or the message or the data we want to encrypt as an array. Once encrypted, we make another call to the backend canister, and this time we want to store this encrypted file as a sort of as a transfer. So we create a request object here containing the recipient address and some metadata for the file, such as the type, the file name, and also the serialized encrypted data. And then we call the backend again with the backend transfer create. This transfer create method, like really briefly, just does some basic validation of the inputs, make sure that the user exists and that the recipient address is well formed, and if all looks good, it proceeds to create what I call a transfer object and stores that in a stable B-tree map. So those are the steps involved in creating the transfer. And now let's move on to look at the other side of the equation, which is when a user that has received the transfer wants to decrypt it. We will once again use a hook. This is a hook that actually calls another hook where we get the encrypted key. So this is important. Let's go and have a look at what that hook does. So get the encrypted key. So me as the recipient, now of course I need to get the full key to be able to decode any transfers that I have received. Now this is a process that more closely mimics the one I showed you in the presentation. Remember that the first part of this process was to generate a transport key, and that this key is an ephemeral, it's a temporary key. So to do that, we just generate a random seed value, and then we call the vetKeys utility library to create a transport secret key based on that seed. With possession of the secret key, we ask the backend canister to now give us the encrypted full key, and supply the backend canister with the public key part of our transportation key. Let's look at the backend canister code. So the vetKeys encrypted key. And one important thing to note here is that we are getting the caller address. I will not go into detail what happens here, but by using the sign-in with Ethereum library, this call means that the backend canister will have secure knowledge about which user is currently authenticated using Ethereum. So basically, this is the Ethereum address of the calling user. And once again, we need to create some arguments to make the system API call. Similar to when we got the public key, we need to specify the key ID, the key name, and the curve. And we again specify an empty derivation path representing this. The whole application uses the same derivation path essentially. And we also, but now at this time, we want to specify the derivation ID, because now we tell the system API which specific key we want. And in this case, that is, again, a byte representation of the Ethereum address of the calling user. The calling user in this case being the recipient of a file transfer. And finally, we have the encryption public key. So that this is the public key part of the transportation key that we just generated. And with these arguments, we can once again call the system API or the testing canister in this case, and basically just pass that information on to the front end. So moving back to the use transfer get hook. We can now proceed to decrypt this encrypted key that we have received. So using the secret key part of the transportation key, we call the decrypt function. This decrypt function, of course, needs the encrypted key to decrypt, but it also requires us to supply it with the public key, this application-wide public key that we retrieved earlier, as well as, again, this byte representation of the user's address, the recipient address, which is the derivation ID. Once we have decrypted the key, we can proceed to use the vetKeys utility library again to run things in reverse. That is, we first deserialize the information, and then we decrypt the information using this now unencrypted key. Once the decrypt call completes, we are now in possession of the full decrypted data of this file. So that takes us to the end of this process. And this is all I had for you today. I'm excited to see what you build using vetKeys, and be sure to like and subscribe to don't miss any more videos like this. See ya!